Can anybody tell me what the acceleration due to gravity is? What you understand by acceleration due to gravity? For a planet like Earth, for example, what does it mean? You must have seen that in your lecture. Someone? What is the acceleration due to gravity?
Are you talking about big G?
So, how do you represent it in your course? There's a big G and there's a small g.
Yeah.
The upper G and lowercase g. Which is which?
The uppercase G is like just the general force of gravity in general, and little g is the force of gravity on Earth.
Okay. Does anybody have a different idea?
The large G is used to calculate like the gravity with respect to like the mass of like or the amount of force applied by like the mass of two different objects, basically.
Yes, that's what it's used for. It was, and what about the small g?
Acceleration due to gravity?
Yes, small one is the acceleration due to gravity. The big one is called the universal gravitational constant. It's a number that's the same everywhere for any two objects that interact gravitationally. Okay, for any two objects that pull on each other, the big G is the same. Okay, so the small g is different for different planets. For the small g for Earth is going to be different from what it is for the moon, for example. And as a matter of fact, it is about for the moon, it is about 1/6 of what it is for Earth. Okay, and it's going to be different on Mars, that small g, and it's going to be different on Mercury, planet Mercury, on Venus, and all the other planets. But the big G is going to be the same no matter what planets you are talking about, no matter what any two objects that are attracting each other you are talking about, whether it's two different stars, whether it's a star and a planet, whether it's a moon and a planet, whether it's a human being and a star, whether it's two human beings, whether it's two pieces of chalk, that big G is always the same. Okay. Yes, it was discovered experimentally by Cavendish. And yeah, you can actually do the experiment yourselves in your own room to see how two objects attract each other gravitationally. Okay, I'm not talking about magnets. Okay, there's no magnetism here. We are just talking about gravity. The fact that the objects having mass will attract each other. Okay, so I suggest that you watch a few YouTube videos. There are very nice YouTube videos that will show you how to do that at home if you are interested. Okay, so the little g now. Okay, the little g. What we are going to call it, it's going to be the acceleration due to gravity, but near the surface of the planet, okay, for our land. So when we say little g, it's the acceleration due to gravity, but near planet Earth, for example, the little g for Earth. For the moon, it's near the surface of the moon. For Mars, it's near the surface of Mars, and so on and so forth. Okay, because in reality, because of Newton's second law, the acceleration changes with altitude. Okay, so with height, with how far away you are from the surface of the planet, the acceleration always changes. So the when we say little g is a constant, that's just an approximation. Okay, near the surface of the planet, yes, it's approximately constant. Right. Well, so what is it equal to on Earth, that little g?
9.8 meters per second squared.
Yes. 9.8 meters per second squared. Okay. And does anybody know its value in pound per? Okay, it's no, feet per second squared. Feet per second squared. Anybody knows value? No. You're not engineering students. I don't remember well, but I think it's 32 feet per. Yes, that's true. 32 feet per second squared. Okay. So okay. So yes, so that's what it is. All right. I think this is a good introduction. Maybe let's see if all right. So I think we can start with the lab. All right. So part one. Okay. So maybe you have your files open, files, the file corresponding to our lab, today's lab, which is lab 3. Okay. It's entitled Measure Little G Simulation Lab. Okay. So the first part will deal with acceleration due to gravity for different planets that have different masses and different radii. Okay, so we start with the first point. Click on URL to open the simulation lab page. So maybe I should share my screen with you. So maybe let me first open the simulation page. Okay, so it's open now. Let me share my screen with you. Okay. All right. So we are told to click begin to start the lab. Can you see the simulation? Somebody tell me if you can see the simulation.
Yes.
Yes, thanks. All right, so click begin. So you see a planet and stars in the background. So click on the ball at the top of the screen. Oh no, click on ball. Okay, so that's a heading ball. Okay. At the top of the screen to change the ball characteristics of your choice. Okay, so we want radius. You can give it any radius you want. Make it small or big, doesn't matter. We're gonna give it 3.5. Okay. What do you want it to be made of? Aluminum, zinc, copper, gold, wood. I'm gonna choose zinc. Why not? Okay. So that's all there is. Now, now we need to click on planet at the top of the screen. I'll go here, I choose planet at the top of the screen and decrease the mass and the radius of the planet to the minimum values. Minimum values is 4. E plus 6 means times 10 to the 6. Okay, times a million basically. So 1 with 6 zeros after the 1. So that's the radius of the planet. So it's 4 million meters. And then what else are we going to do? So decrease mass and radius of the planet to minimum possible. I'm going to decrease the mass. Notice that as the mass changes, the density changes too. What is density by definition? What do you understand by density of a planet?
It's the mass divided by the volume?
Yes. It's an entire mass divided by entire volume. Yes. So in this case, we say that what we are calculating is the mass density. So the mass density of our planet is 2,238.1 kilogram per cubic meter. Okay. Choose a name for it. Okay. So planet name, Tatooine is nice. Okay. Remember that from the Star Wars movies. Or you can keep changing until you stop with the name that you like. And the color, you can change the color. This green maybe, or a yellow planet, red planet. I don't know, it doesn't matter. Green. Is it purple? Yellow looks weird. Yeah, this color, orange. Okay. Then click zoom in and click on the ruler. Okay, zoom in is here. We are getting closer and closer to the planet. We have landed on it. We are sitting on the surface of the planet. We're standing on the surface of the planet. Now we need to click on ruler and bring the ruler. Okay. Now we need to place the ball at 4.5 meters height. Okay, 4.5. Let me change the characteristics of our ball a little. Okay. I don't want it to be made out of zinc. Maybe plastic. Yeah, maybe just plastic. Okay. All right, plastic. Bring back the ruler. So we need to place our ball at 4.5 meter height. Okay.
Yeah.
Yes. Okay. So now we need to click on drop the ball. Okay. On drop, and it falls. Okay. You saw it fall. And then we click on grid at the bottom of the screen, and we see how the velocity or the speed in this case changed as time went by. Okay, that's represented by this graph. And then you have to record data on the velocity and time, okay, for your lab report. Now we need to click reset for an opportunity to make another run of the experiment with the same planet mass and radius setting. So first I click in the grid, and then click reset, and then I can drop the ball again. Click drop, and it falls. Okay, and I get a new grid, a new graphical representation with different values for speed and time. And then you will have to compute the average, right? Now we need, I'm at point number 10. I'm reading the instructions from the file. So I'm at point number 10. So we need to click reset and zoom out so that we can pick a different planet. Zoom out. Okay, so we're leaving the planet and we are going to choose another one. So which one do we choose? We go to the planet option, the planet section. Click planet. Okay, we need to increase the mass and the radius by 1 upward, upward arrow click. So I increase the radius to 4.5 and the mass by 1 to 7. Okay, and record the new name of the planet, mass, radius, and density in table 1. So we need to a new name. So instead of Tatooine, Gallifrey. So that's my new planet. Okay, and then you need to record all of this in the table. And then you need to repeat steps 5 through 10 above until there are 6 different planets. So this is the second planet. So we need to go to drop the ball once more, but then carry out the experiment twice so that we can compute an average for this specific planet Gallifrey. And then we will choose a third planet. Okay, you will increase the radius by 1, you will increase the mass by 1. The density, of course, will change, and you'll give it a new name, and conduct the experiment again, okay, by dropping the ball twice, okay? And then you keep doing this and over and over until you reach the sixth planet, okay? After the sixth planet, you will be done with point 11, and then you can move on to point 12, which will consist in plotting a graph of the average speed against the average time. And then you will have to determine the slope of this graph. And you will tell us what the slope of this graph means to you, what it shows, what it represents. And that's the first part. Are there any questions with this first part? Oh, there's a 13th point, which says plot a graph of the planet mass versus the planet radius squared, and determine the slope of this graph. What is the significance of the slope times 1 over g? I believe they meant slope times big G instead of slope times 1 over g. Do you all see that on the third page? 13th point, still in part 1?
Yes.
Yeah. Change that 1 over big G to just big G. That's what would make sense. I did the calculation and I found that if you write big G, then it all makes sense. But if you write 1 over big G, then it doesn't quite make sense. Unless, let me see. Unless you plot planet radius squared against planet mass, then what they said would make sense. Would it? Let me see. Yeah, it would kind of make sense. Yeah, so I think in order to make your life easier, just replace 1 over G, 1 over big G by big G. Okay, that would take care of the problem. Okay. Are there any questions so far? No? Now we can start part 2 if there are no questions, which is called Exploring Acceleration Due to Gravity on Planets with the Same Radius but Different Mass. Okay? So if I keep the radius of the planet constant, so I don't change the radius of the planet, what will happen to its volume? Since they are spherical, the volume doesn't change. It won't change, of course, because the volume of a sphere depends only on the radius. It's 4 over 3 pi r cubed. So it depends only on the radius. So if I keep the radius the same, the volume of the planet doesn't change. Okay? So what could change? The mass could change. Okay? If the mass changes, what happens to the density of the planet? Let's say the mass increases. What happens to, and the radius is kept constant. What happens to the density of the planet? Anybody has any idea? So let me repeat my question. You keep, so you have take a sample of 10 different planets, but they are all of the same size. So they all have the same radius. But their masses are different, and there are ways of computing the mass of a planet. Okay? their masses are different. In that case, what happens to the density of the planet? Let's say so from planet A to planet B, the mass has increased. The mass of planet B increases. Its density will be, I think somebody said.
It would get smaller.
So if the mass increases, the density will get smaller.
Yeah, because they're inversely related. No, sorry. Mass over volume. Sorry, it would get bigger as well.
Yeah, the density would increase. That's correct. The density would increase. That's true. That's true.
Also, there's somebody asking questions in the chat. I'm just wondering, can you see the chat or is it not visible on your screen?
Yeah, I can see it, but there are many questions. So let me see. What is the question? So we can start off from whatever we want and just add 1 to 8 6 times. Yeah. Well, no. So for part 1, you have to start from the minimum, right? You are told in point number, was it the second point, fourth point? Fourth point, click on planet at top of screen, decrease mass and radius of planet to minimum possible. So you have to start from the minimum and then increase by 1 6 times. Okay. Yeah, I'm sorry for not answering your question because, yes. So that's what you can do. Okay, so that's what you have to do. You have to start from the minimum possible and then increase by 1 each time. All right. Okay. All right. Any other questions? No other questions? Then we can start with the second part. So exploring acceleration due to gravity on planets with the same radius but different mass. Okay, so now we're going to have a collection of planets that all have the same radius. Therefore, they all have the same volume. They all have the same size. But the mass will change. And as your classmate pointed out so well, if the mass increases and the radius is kept the same, then the density will increase. Okay, the density will increase. Okay. Now, the first point says click on planet at the top of the screen. Okay, planet. Click on it. Decrease the mass and radius of the planet to the minimum possible. Oh, I was already on it. Sorry about that. Minimum, so I'm already there. Oh, no, mass, minimum. I've reached the minimum possible. Okay, so choose a name. Okay, choose a name, planet name, Cobalt. Why not? I'll call it my planet Cobalt. And that color. I want it to be purple. And then you will need to record the information in the table. Then the second point, click zoom in, then click on ruler. So I want to go and land on my planet, the planet I've chosen. I'm standing on it now. And then click on ruler. So I need to bring a ruler so I can make measurements. So now I need to click I need to place the ball at 4.5 meter height, which it's already there. Okay, and then drop the ball to begin the first run of the experiment. I click on ball and it falls down. Okay, and I get a graph, and I get a graph here that tells me, that shows me how the speed changed with time. Okay. All right. So now the speed changed with time. So what do I need to do next? So click on the grid. I just did that. And I need to record the data on the velocity and time. Then I need to click reset in order to make another run of the experiment with the same planet. Okay. So I have to click on the grid first, click on reset, and then click on drop once more. And the ball drops, falls, and I get new values for speed and time. Okay. And then you will need to record the data in the table 2. So now we need to pick another planet. Okay. We need to click this reset first. Okay. Zoom out. Oh, sorry. So reset, zoom out. I leave my planet and I choose another one. But remember, for the second part of the lab, we are making all our planets, we want them to have the same size. So we're keeping the radius the same, and all we are doing is change the mass. But we have to increase it by only one click. Okay. And then you have to change the name because now we are going to study a different planet. No. Yeah, color also. Green maybe Kronos or Alderan. Okay, whatever you want name. Arrakis. That's gonna be my new planet name. Okay. And then as you can see, we are not changing the radius. Okay. But we're changing everything else. And then you repeat the steps. Okay. You drop the ball, so let me do it at least once. Okay. Zoom in, go to my planet, my green planet. I think I like this. Okay. Then I need a ruler. I need to place the ball at 4.5 meters and then drop it. Falls down, and I get a new graph of speed versus time. Okay. And then I need to do this I need to conduct this experiment a second time, that is drop the ball a second time. And then once I have the data and I have recorded the data, I can go and choose a third different planet, okay, by just increasing the mass this time. And I need to do this 6 times, okay, until I get the data that I want. Now I'm on point number 9. So by increasing the planet mass but maintaining a constant radius, you are in effect increasing the planet's density. Okay, but that you already knew because you answered the question earlier. What effect did this increase in density have on the average time for the ball to fall through 4.5 meters? So you don't have to answer that question while working on your lab. Okay, point 10, plot a graph of average velocity versus average time and determine the slope of this graph. What does the slope of this graph tell you concerning the relationship between acceleration due to gravity on a planet and increased density? So you will have to think about this and work on this when you have more time. And then question 11, what is the name of such a body or planet or star which is so dense that it is difficult or impossible to escape its gravitational force of attraction? Okay, so you have to do some research for that. Okay, and then number 12 is some plot that you will have to do. Okay, and then that's it. And that's the end of the lab. And you see that, as I told you, it's a short lab and a rather easy one too. So are there any questions?
Professor, can you go over how to fill out table 3?
Well, that's point number 12. It says, so check accuracy of your data points in the graph produced from table 2. So you're basically checking that your work in table 2 is correct by using a linear equation of motion. You've seen this equation, right, for constant acceleration. dy equals v t average plus 1/2 g planet time squared. You must have seen that, right, in class during your lecture for constant acceleration. Okay.
Yes.
Yes. dy is the vertical distance fallen. It's just that the variables that you used may have been called different names. Okay, vi is the initial velocity and t is time to fall to the ground level. Okay, but now for us, because we dropped the balls, okay, instead of throwing them, so basically we just let go of them. Okay, so the initial speed was always 0. Okay, so because we did not actually throw them, so vi is the initial velocity will be 0. Okay, and t is the time to fall to ground level. In our experiment, the ball was dropped 4.5 meters for all our experiments, meaning initial velocity is 0, as I just mentioned, and so the shape of the equation is simplified in that case because one term becomes 0. Okay, and from the resulting equation, the simplified equation, you can solve for g, the acceleration due to the gravity of the planet, and that's what you have here. Okay, so we wanna find that acceleration due to gravity and compare with the data we got from table 2. Okay. So what we're going to do is just use the data on V average and T average and use that to compute the acceleration due to gravity and compare the answers with what we get in table 2.
Okay, that makes sense. And just to make sure, so from part 1, the information regarding the ball radius and the ball material remains the same throughout, right?
Yes.
Okay, thank you.
Any other question? Okay, I think it's better if you start working on the lab, and when you get questions, you can ask me, and I will answer your questions. So I'm going to stop recording now.